So let us start with scattering theory. Okay, so this is the foundations for basically analyzing wave networks, right? Rather than getting into the complex details of the mode patterns and the electric and magnetic fields themselves, we are going to look at some quantities which we are going to call wave amplitudes in order to make some simplifications and make the formalism more general in order to accommodate multiple components. Right? Remember, we only calculated the fields as solutions to a rectangular waveguide. Right? Now, if I were to say bring in some interruptions, right? One way to design filters is actually to insert various discontinuities within the rectangular waveguide, right? As metallic rods in very specific locations at certain depths, right? So if we were to analyze these situations, it can quickly get exceedingly complex, right? So in scattering theory, we start by saying that electric and magnetic fields are the fundamental quantities. Okay. Voltages and currents in circuits are manifestation or derived quantities. Right, but nonetheless remember the power of using voltages and currents during transmission lines, right? They were scalars, they were not vector fields, and they were only single dimension, right? So it made circuit analysis so much more elegant, right? So we are taking clues from the fact that the study of transmission lines gave us a way of moving away from the electric and magnetic field pictures, which were vector fields, right, or four dimensional, to two dimensional, that is one spatial and one temporal dimension for voltages and currents, right. So let us see if we can bring that analog over here also, right. Okay, so we define ports 1, 2, 3, 4, right. And since we described voltages and currents as wave like quantities, right, so we are going to say that there are wave like quantities. We'll define what these A's and B's are very shortly, but each port brings in electromagnetic energy in the form of waves, right? And there are waves both injected into the port as well as waves going in the opposite direction, right? So we'll use the letter A for injected waves and B for waves that are exiting the port, right? So similarly we can say there's A2 and B2, A3 and B3, and let's call this port N, right? I have AN, BN, right? And if I am accounting for all the inputs and outputs perfectly, right, and there's no loss, I can actually say that the output coming from any particular port J is essentially the summation let's call this port I running through J, Sij, Aj, okay. So this S that I have written is a scattering junction, right? So it's a junction of where the ports 1 to n, right, interact with this complex junction. This junction S could signify anything, right? So for example, we are going to be looking at simple 2-port devices, right? So there can be amplifiers, they can be filters, right? Can even be a simple waveguide, right? So whatever it be, right, we can define ports, right, and we can talk about the wave amplitudes that are injected and exiting these ports, right? And if I were to make a good accounting book of all the powers coming in and leaving, right, I should be able to make this statement, right? That is, the power or wave amplitudes leaving a particular port, right, is essentially the sum total of all the incoming signals, right, and is being scattered at this junction, right? So the process of scattering is used, and the word scattering is used because remember, when there's a beam of light that hits the surface that is scattering this light off, you will notice that you will be able to see this scattering at any angle, right? So similarly, if there is some energy coming in through one port, the scattering matrix can essentially redistribute this energy into all the available exit ports, right? So if I say I is my exit port, Bi, the wave amplitude that is leaving that port I, is essentially all the incoming waves getting scattered and redistributed, right? And Sij is essentially saying how much fraction of the wave amplitude that was injected in port J ends up in port I. Okay, so the order of these subscripts Ij is reasonably important, right? So I is the output port, okay, and J is the stimulus. Okay, so what can I say is the definition for Sij? It's essentially Bi by Aj given Ak equal to 0 for all k not equal to j, right? So if I were to not inject any wave amplitudes in any of the ports except the jth port, right? So only Aj is non-zero. All the other ports, there's no input wave amplitude, and I ask the question, how much of this wave that was input in the jth port shows up in the ith port, right? So Bi divided by Aj is essentially Sij, right? I still haven't told you what A and B are. I'll cover that very shortly. Okay, but this is the formalism. This is the formalism that we are creating. We are saying that there is a scattering junction that essentially redistributes energy coming from any port to all ports. Okay, if there is no contribution from say port 1 to port 3, that scattering parameter, right, going from S3 1, right? So I look to excite from port 1 and measure at port 3, right? So S31 will essentially be 0 if there is no contribution, right? But in general, the scattering matrix allows for energy from any port to be redistributed to all the ports, right? In fact, it can come back to the same port, right? So in fact, there is nothing wrong with setting j equals I, right? So I injected a particular port and I ask how much is coming back or reflected back into the same port, right? So now I am going to define what these AJs and Bs are, right? So we are going to say that A and B are wave amplitudes, right? and they are so defined such that the square magnitude gives us the power, right? So we are going to say that Aj is Vj plus phasor divided by square root of 2Zj. This is in the case of transmission lines where we are dealing with voltages, currents and characteristic impedances. In the case of plane waves and modes, we can define Aj as Ej going in the direction of the input, right? This is also a phasor divided by square root of 2 eta j. Okay. And we can say similarly Bj would be the E minus, right, or V minus. Okay. Okay. So whether it is voltages and currents in transmission lines or fields of plane waves or modes in a rectangular waveguide, one can always define these A's and B's in such a manner, right? Once we do this, we can notice that the net power flowing into a port can be defined as Pj is Aj star minus Bj star. So what is Pj? It is the average power flowing into port J. Okay, you can also verify this for a plane wave. You know that if I have an electric field of magnitude E naught, right, the average power flow is 1/2 E squared by eta, right. So you can see that if I take Aj and multiply it with the complex conjugate or mod A squared, it essentially gives me the average power carried by the positive propagating wave, and Bj is that of power flow going in the opposite direction, the net of it being the net power, average power that's flowing into the port, right. So these are just definitions, right, in this formalism. Remember, this is slightly different. So Sij, which is the ratio of these wave amplitudes, is slightly different from the field reflection coefficients and field transmission coefficients, right. So let's keep that in mind, right. So that's the reason to spend some time in elaborating this theory, right. You may see there are parallels and that some scattering parameters may actually equal some of those field transmission and field reflection coefficients, but in general they are not the same. Okay, scattering parameters are parameters of their own, right. One may be able to equate some of these scattering parameters to gamma t, right, but in general these A's and B's are new quantities, right, that I am defining, such that the square magnitude of these wave amplitudes give the average power flow. Okay. So let us move our focus from rather an n-port scattering theory to a simple linear two-port components, right. So I only have two ports, port number 1 and port number 2, right. So I can now draw A1, B1, A2, B2, sorry, remember that A's always signify power coming into the port, right? And B signifies power leaving the port, right? So an arrow mark moving towards the device is usually denoted with the lowercase a, right? And the power that is leaving the device in both ports, right, is with lowercase b. So scattering theory relates these quantities in this manner. S, let's say B1, B2, S11, S12, S21, S22. Okay, you can essentially think of that A is all the powers that's coming to the device and B is all the power that's getting scattered off, right? So the power that is scattered off from the device is related to the power that's coming into the device through the scattering matrix, right? So we are calling this the scattering matrix. So the scattering matrix is of the form of a 2 by 2 matrix because there's only 2 ports, right? One can also have an n by n scattering matrix for n ports, right? So in this we can make some simple conclusions or statements, right? That is, if I have a reciprocal system, right, that the off diagonal elements are the same, S12 and S21. This is to say that if energy were injected from port 2 and collected in 1 or injected into port 1 and collected in 2, there's not much of a difference, right? This is what we call a reciprocal system. And if we consider the lossless nature, right, that is, all of the power from A1 and A2 ends up in either of B1 or B2 or a combination of both, right? In that case, we can say that in a lossless 2 port, we can say S11 squared plus S21 squared is 1. Similarly, S22 squared plus S12 squared is also 1. Okay. So the first statement is saying that if I were to inject some power in port 1, right, and I were to send no inputs through port 2, that the energy that is coming into port 1 would have to redistribute itself into port 1 or 2. That's the only 2 options for it, right? This is what a lossless 2 port network is, right? There's no mysterious energy being lost in this wave network, right? So when I launch in 1, you can see that the second subscript is the same, and I collect the energy in 2 or 1, right? And if I do the modular square of these scattering parameters, I'm actually getting power, right? So the sum total of the power that I measure in port 1 and port 2 while injecting power only in port 1 and not port 2, right? This sum has to be 1, right? Similarly, if I were to inject power through port 2, it has to either end up in port 2 itself or should get transmitted into port 1. Okay, that's all the power conservation law is saying. So we can just call this power conservation. Okay, so let us try to expand these. These are actually just linear equations, right? So equation 1, although written in a matrix form, one can simply write this as B1 is equal to S11 A1 plus S12 A2. Similarly, B2 is S21 A1 plus S22 A2. Right? So you can also see the definition for the S matrix that we saw in the previous slide of Sij being the ratio of Bi by Aj, right? Given that all other A's are 0. So even here, if I wanted to know what is S21, S21 is essentially B2 by A1 given A2 is 0. Right? So hopefully you can understand the definition of the scattering matrix in the previous slide for this simple two-port system. Okay. So another useful transformation, right, is to look at the same two ports but relating the A's and B's slightly differently, right? So we call this the transmission matrix. It's just a mathematical rearrangement. Okay. And it is particularly useful when we start cascading elements, right? We will see this very soon. So I have the same two-port device, right? And instead of relating all the incoming waves to the outgoing waves, we are going to relate all the waves which are on one port to the waves that are in the other port, right? So this is what we called as B2 and this is A2. Okay. So we'll define the T matrix this way. So we are going to write A1 B1 is equal to T11 T12 T21 T22 times B2 A2. Okay. So I'm kind of using a notion of a left-right system, right? So A1 is the wave amplitude going to the right, B1 is wave amplitude going to the left, right? Similarly, B2 is the one going to the right, A2 is going to the left, right? In the scattering viewpoint, we only looked at A's being the amplitudes that come towards the element, right? And B as the variables that are taking power away from the element, right? This actually lends for some very nice intuition, right? So when I say that I am injecting some power into the port and that some power is actually coming back or it is being transmitted through, S parameters is very comfortable way of communicating these kind of information, right? But we'll notice that the transmission matrix formalism actually benefits us when we look at cascading multiple ports, right? So if I'm looking at a two-port element and a second two-port element and I would like to, right, sort of couple them, and I would like to ask the question what happens from the input to the output after I couple both the elements together, right? So the two together would form a comprehensive two-port device, right? And I can talk about the input-output features or input-output properties conveniently, right? So because of the way matrix multiplication works, trying to move to a transmission matrix formalism where we look at signals going right and left, right, has some direct advantages, right? The reason I say that is I can have a transmission matrix TA for the first two ports and TB for the second two port, and I can say that this can be equated to a single composite two port element whose transfer matrix or transmission matrix is simply TA multiplied by TB. Okay, you can prove this to yourself, right? So you can have A's and B's at each of these ports, right? And you can notice that these two are essentially the same. What is ejected out of port 2 from component A is actually the input to port 1 of component B, right? So you can represent this matrix as another transmission matrix multiplied by the AB values at the output of the second element, right? So it is very easy to cascade transmission matrices one after the other in order to get the composite response of a chain of elements. Okay, so transformation matrix formalism lends itself to conveniently cascade many components together and looking at the overall property, right, of the entire chain. So as students, it's important to know how to go back and forth between the transmission matrix formalism and the S matrix or S parameter formalism, right, the scattering matrix formalism. So we can do that, right. So the equations here relate A1 to B2 and A2. This T11 B2 plus T12 A2, and I have B1 is equal to T21 B2 plus T22 A2, right. Remember, A's and B's are the unknowns, right, and they are just variables that can basically be moved around, right, in these linear equations, and I just need to ensure that I get an equation similar to these two in order to equate the coefficients, right, and say the relation between the S and T matrix. So let us do one very quickly. So I need A1 on the left hand side. So let us take this equation. This becomes A1 is equal to 1 over S21 B2 minus S22 by S21 A2. Okay, so I can see that I have now A1 on the left hand side and B2 and A2 on the right hand side. So I'm just going to compare this equation and this equation, right, and I'm already readily getting the relationship between some of the elements. Okay, so what can I say is T11 is simply 1 over S21 and T12 is minus S22 by S21. Okay, in order to get the T21 and T22s, I can actually just substitute this into the first equation for A1, and I will have B1 in terms of A2 and B2 only, right. So that will yield B1 is equal to S11 by S21 B2 minus S11 S22 by S21 A2 plus S12 A2. Okay, so comparing these two equations, we can say that T21 is quite simply S11 by S21 okay, and T22 is actually S12 S21 minus S11 S22 divided by S21. Okay, so for those who have done some matrix analysis or matrix theory in the past, you may be able to recognize the numerator here, right. For a 2 by 2 matrix, that is actually the negative of the determinant, right. So I can also write T22 as minus determinant of S divided by S21. Okay, so the determinant of S is essentially S11 S22 minus S12 S21. Okay, so I take the main diagonal elements, multiply them, take the off diagonal elements, multiply them, and take the difference of the two. Okay, so let us formalize this, right. So I am going to say that the T matrix in terms of S parameters becomes 1 by S21 1 S11 minus S22 and minus determinant of S. Okay, even if you don't remember this, you know how to derive this, right. So this is the transmission matrix given the scattering matrix. We can also go the other way around. So if you want the S matrix or the scattering matrix in terms of the transmission matrix, we can say that it is simply 1 by T11 T21 determinant of T 1 and minus T 1 2. Okay, so as students at this point, you should very well understand what is scattering theory, what are wave amplitudes A and B, how are they defined, the modulus square of A and B signifying the average power flow in a certain direction, and that we have two kinds of matrices that relate for a simple two-port device, right, the scattering matrix and the transmission matrix, and how to relate the individual elements of these matrices with each other, right. So this is all the topics we have covered so far, and is going to be very crucial in solving some very simple problems that we are about to see.